Earth's 2 billion-year-old nuclear reactor, the impossible reactor. 2 billion years ago, long before the first humans walked the Earth, before the rise of mammals, before even the first complex plants took root on land, deep within the crust of Africa, something extraordinary was happening. In a remote corner of what is today Gabon, a chain reaction was underway. A nuclear reactor was running, not in a laboratory, not in a power plant, but in the Earth itself. No control rods, no engineers, no technology, just rock, water, and the laws of physics. That is not science fiction. It is one of the most baffling discoveries in modern science. A natural nuclear reactor, operating long before human civilization ever dreamed of splitting the atom. Known today as the Oklo reactor, it challenges our very understanding of what is possible. How could the Earth itself build a power plant? How could natural processes mimic what we only achieved in the 20th century, after decades of research and the genius of minds like Einstein and Fermi? And what does this ancient reactor reveal about the hidden powers of our planet? The story begins not in prehistory, but in 1972. In the small mining town of Oklo, French scientists working for a nuclear fuel company analyzed uranium ore extracted from the region. What they found stunned them. The uranium samples did not contain the normal amount of uranium-235, the isotope that fuels nuclear reactions. Instead, it was depleted, as if it had already been burned in a reactor. At first, they suspected theft or secret weapons work. But soon the truth emerged. The fuel had not been stolen. It had been consumed 2 billion years earlier by a reactor that nature itself had built. Think about what that means. In our world, nuclear power is the product of immense knowledge and technology. We enrich uranium, we moderate it with water, we control the chain reactions with rods and shielding. Yet in Gabon, deep underground, all of those conditions had once aligned perfectly, with no human hand guiding them. Uranium deposits naturally contained a higher concentration of uranium-235 than they do today. Water from underground rivers seeped into the rock, acting as a natural moderator. And the geometry of the ore itself allowed fission to sustain, starting, stopping, and restarting in cycles that may have lasted for hundreds of thousands of years. For scientists, this was a revelation. A natural nuclear reactor operating billions of years ago was not supposed to be possible. Yet here it was, undeniable evidence written in the chemistry of the rocks. Oklo had achieved what we once thought only humans could, controlled nuclear fission. And it had done so in a world utterly alien to ours, a world of primitive oceans, shifting continents, and a young Earth still shaping itself. The Oklo reactor forces us to ask questions that push beyond geology. Was this truly a coincidence? A perfect storm of conditions that happened only once in the history of the planet? Or could it suggest that nuclear processes might occur naturally elsewhere, in other times, or even on other worlds? Some have wondered if Oklo was simply nature's experiment, a reminder that the universe holds secrets we have only begun to grasp. And then there are the implications. Oklo shows us how uranium behaves over billions of years, how radioactive elements can remain stable and contained in natural rock. For scientists studying nuclear waste storage today, Oklo is a priceless laboratory, a window into the deep future, where questions of safety and time are measured not in centuries, but in eons. But beyond the science lies the mystery, because Oklo should not exist. It defies our intuitions, blurs the line between natural and artificial, and forces us to rethink the boundaries of possibility. How could a world without intelligence, without planning, without design, produce something so precise? Was it luck? Was it inevitability, or was it something else? Tonight we will journey into this mystery. We will explore the discovery of Oklo, the mechanics of how a natural reactor could function, the ancient world that made it possible, and the lessons it holds for science and philosophy today. Along the way, we will confront questions that reach beyond physics, about coincidence, about the hidden order of nature, and about our place in a universe that may be stranger than we dare to imagine. Because if the Earth itself could build a nuclear reactor 2 billion years ago, long before life as we know it even existed, what else might it be capable of? Discovery at Oklo. Our story truly begins in 1972 in the West African nation of Gabon. At first, it seemed like nothing more than routine business. The French nuclear energy company, Kojima, was mining uranium ore from deposits near the small town of Oklo. For France, uranium was critical. It fueled their growing nuclear power program, providing the energy of the future. Every shipment was carefully measured, every sample meticulously analyzed. But one day, something was off. Scientists in a French laboratory noticed that the uranium ore arriving from Gabon didn't look quite right. When they tested its composition, they made a startling discovery. The uranium contained less uranium-235 than expected. Normally, natural uranium contains about 72% uranium-235, the isotope that sustains nuclear chain reactions. Yet the Oklo samples had only about 0.60%. That might sound like a small difference, but in nuclear science, it was enormous. At first, suspicion spread. Had someone tampered with the uranium? Was there secret diversion, perhaps for weapons? After all, the Cold War was in full swing, and the idea that uranium had gone missing raised alarms. For a time, it seemed like the scientists had uncovered a scandal. But as they dug deeper, the truth that emerged was far stranger. The uranium wasn't stolen, it had been burned. The isotopic signature of the Oklo ore looked exactly like fuel that had already gone through a reactor. Certain fission byproducts like neodymium and ruthenium appeared in the samples in ratios identical to those produced inside modern nuclear plants. But this was impossible. At least, it should have been. No nuclear reactor had ever been built in Gabon. And even if one had, it certainly could not have been operating 2 billion years ago. The scientists were stunned. The evidence was undeniable. Natural uranium at Oklo had undergone sustained nuclear fission in the past. Somehow, the Earth itself had created conditions identical to those inside a man-made power plant. As the realization spread, excitement rippled through the scientific community. This was not merely a curiosity, it was a revelation. Oklo was a natural nuclear reactor, one that had functioned billions of years before human beings even existed. The discovery shook nuclear science to its core. News spread quickly beyond France. Physicists, geologists, and nuclear engineers from around the world flocked to Gabon, drawn to the mystery. How could this be possible? What conditions could allow natural uranium deposits to act like a carefully designed reactor? Was Oklo unique, or were there other hidden reactors waiting to be discovered beneath the Earth's surface? The answers began to emerge slowly. 2 billion years ago, the concentration of uranium-235 in natural uranium was far higher than it is today. Because uranium-235 decays faster than uranium-238, its proportion has declined over geological time. Back then, it made up about 3% of natural uranium, almost identical to the enrichment used in modern nuclear reactors. That coincidence alone was extraordinary. But enrichment was not enough. For fission to sustain, a moderator was needed, something to slow down the neutrons and keep the chain reaction under control. At Oklo, that role was played by water. Underground aquifers seeped through the uranium deposits, moderating the reactions just as engineers use water in modern reactors. And the shape of the ore, its geometry and density, allowed the reaction to continue in a self-sustaining cycle. What the scientists pieced together was astonishing. The Oklo reactor may have run intermittently for hundreds of thousands of years. When the reaction heated up, the water boiled away, stopping the chain reaction. Once the rock cooled, water seeped back in, and the reaction began again. Start, stop, start, stop. A natural cycle of nuclear fission, repeating endlessly, long before humans had even evolved. The implications were profound. For the first time, humanity had proof that nuclear fission was not an artificial invention, but a natural phenomenon. What we had harnessed with reactors and bombs was, in fact, something the Earth itself had once produced spontaneously. The discovery also carried a more practical lesson. By studying the Oklo deposits, scientists could see how radioactive byproducts behaved over billions of years. Some elements, including plutonium, had formed in the reactor and remained locked in place, barely moving in all that time. This offered hope for modern nuclear waste disposal. If nature could contain dangerous materials safely for 2 billion years, perhaps humans could too. But beyond the science lay the mystery. A mystery that still lingers. Why Oklo? Why there in Gabon and not somewhere else? Was it truly a one-time accident of geology, never to be repeated? Or did it reveal a hidden principle of the Earth, a tendency toward order and complexity that we are only beginning to glimpse? Standing at the site today, you see nothing but quiet mining pits, grass growing where ore was once extracted. Yet beneath your feet lies the memory of a power plant older than life itself, its secrets written in the isotopes of stone. Nature's reactor. To understand the magnitude of what happened at Oklo, we must first step into the heart of a nuclear reactor itself. At its core, nuclear fission is simple to describe, but extraordinary in power. When an atom of uranium-235 absorbs a neutron, it splits into smaller fragments, releasing more neutrons and a burst of energy. Those neutrons can strike other uranium atoms, splitting them in turn, cascading into a chain reaction. In a controlled environment, that chain reaction generates steady heat, enough to power turbines, cities, and nations. In an uncontrolled environment, it becomes a weapon of devastating force. Human beings learned to master this process only in the 20th century. In December of 1942, under a squash court at the University of Chicago, Enrico Fermi and his team created the first artificial nuclear reactor, Chicago Pile 1. It was a fragile, primitive assembly of graphite and uranium, tended by anxious physicists who feared the unknown. And yet, nearly 2 billion years earlier, in the rocks of Africa, nature had already achieved the same thing. Without blueprints, without calculations, without human hands. So how did it work? The answer lies in the unique conditions of the ancient Earth. 2 billion years ago, the ratio of uranium-235 to uranium-238 was far higher than it is today. In modern times, uranium ore contains less than 1% uranium-235, not enough to sustain a chain reaction naturally. But back then, uranium-235 made up about 3% of natural uranium, the same enrichment we use today in commercial power plants. That enrichment level was the first piece of the puzzle. The second piece was water. Flowing underground, seeping into cracks, it became the perfect moderator. Neutrons released during fission are born fast, too fast to efficiently trigger more fission events. Water slows them down, turning a runaway process into a sustained, steady rhythm. In man-made reactors, we design elaborate cooling systems and control rods to manage this balance. At Oklo, groundwater did the job automatically. The third piece was geometry. For a chain reaction to persist, the uranium must be arranged in the right way. Too scattered, and neutrons escape before hitting another atom. Too concentrated, and the reaction flares uncontrollably. At Oklo, the ore deposits were just the right size and shape. layers of sandstone and clay acted as natural barriers, keeping the reaction zones confined. It was as though the Earth itself had designed a reactor core. What emerged from these conditions was astonishing: a self-regulating nuclear reactor operating in cycles of fire and water. Scientists believed the process unfolded like this. The uranium began to fission, heating the surrounding rock. As temperatures rose, groundwater boiled away, removing the moderator and halting the reaction. The system cooled. Water flowed back in, slowing neutrons once again, and the reaction reignited. On and on, this cycle repeated, perhaps every few hours, like the slow breathing of the Earth. For hundreds of thousands of years, the Oklo reactors pulsed with this rhythm. 20 distinct reactor zones have been identified in the region, spread over an area several kilometers wide. Together, they may have produced an average power output of 100 kilowatts, small compared to a modern plant, but remarkable for a natural phenomenon. Enough to light a small town today, humming beneath the surface of the ancient Earth. The evidence of this operation is etched into the rocks. In the isotopes of neodymium, ruthenium, and xenon, byproducts of fission, scientists find fingerprints identical to those in reactor fuel rods. Even traces of plutonium have been discovered, formed during the reactions and captured in the mineral matrix. Incredibly, those elements have barely migrated in 2 billion years. They remain locked in place, proof that the Earth not only created a reactor, but also managed its waste more effectively than any technology we have devised. This natural reactor was not a brief spark. It endured. It ran for hundreds of thousands of years in cycles of reaction and rest, generating energy long before animals, long before forests, long before humanity. In a world dominated by single-celled life, deep underground, a nuclear heart was beating. The sheer improbability of it is staggering. For all the conditions to align, the uranium concentration, the presence of water, the perfect geometry, it seems almost impossible. And yet, it happened. Oklo stands as a reminder that the laws of physics can conspire in ways that mimic design, producing order and complexity where none is expected. And here is where the mystery deepens. If Oklo could exist on Earth, could similar reactors exist elsewhere? Could natural fission occur on other planets, in other times, hidden in alien geology? Or was Oklo a singular miracle, a once-in-a-planet event that can never be repeated? What is certain is this: Oklo was not an accident. It was the inevitable consequence of the Earth's chemistry and geology at that moment in time. Nature itself built a power plant, tended by nothing but stone and water, cycling on and off for eons. The ancient world, 2 billion years ago. To understand why the Oklo reactors could exist 2 billion years ago, we must first imagine the Earth as it was then. The world of the early Proterozoic era was almost unrecognizable compared to today. Continents were smaller, clustered into primitive cratons, drifting slowly on a restless planet. The air above was thin and strange, the oceans below teeming not with fish or corals, but with microscopic life, bacteria, algae, and the first stirrings of complexity. Life was still young, the Earth still raw, and yet deep underground, a nuclear fire was burning. 2 billion years ago, the composition of uranium was different. Uranium-235, the isotope that fuels fission, decays faster than its heavier cousin, uranium-238. As time passes, the proportion of uranium-235 declines. Today it makes up less than 1% of natural uranium, far too little to sustain a chain reaction on its own. But in the ancient Earth, uranium-235 was far more abundant. Back then, it accounted for about 3% of natural uranium, almost exactly the same level we artificially enrich it to in modern reactors. By sheer coincidence of physics and time, the early Earth carried the perfect fuel. The environment of the Proterozoic also contributed to this unlikely miracle. Plate tectonics was already shaping the land, creating basins where uranium ore could accumulate. Groundwater moved freely through the rocks, seeping into cracks and crevices, circulating slowly across ages. And above all, the atmosphere was undergoing one of the most profound transformations in Earth's history, the Great Oxidation Event. Before this event, the Earth's atmosphere had almost no free oxygen. Life was dominated by microbes that thrived without it. But around 2.4 billion years ago, cyanobacteria, tiny blue-green algae, began releasing oxygen as a byproduct of photosynthesis. Slowly, over hundreds of millions of years, oxygen accumulated in the air and the oceans. This transformation altered the chemistry of the entire planet. Uranium, normally soluble in water, was oxidized and precipitated, concentrating in sediments. Without the rise of oxygen, the rich uranium deposits at Oklo may never have formed. Imagine that world. The land was barren, lifeless rock washed by shallow seas under a dimmer sun. The air held far less oxygen than today, unbreathable for us. Storms swept across young continents, lightning flashing over endless horizons. And deep beneath the surface, uranium-rich rocks gathered in seams, waiting. As water seeped through them, the conditions were quietly, inexorably aligning. The stage was being set for a phenomenon that would not be seen again for billions of years. It was in this world that the Oklo reactors were born. The high concentration of uranium-235, the presence of water, the geological structure of the ore, all of it came together in a fragile balance. When the first chain reaction began, there were no eyes to witness it, no minds to comprehend it. The only life that existed was microbial, drifting in ancient seas or clinging to rocks in thin films. Yet beneath their feet, the Earth itself had built a power plant, running on cycles of fire and water. This perspective makes Oklo even more extraordinary. For us, nuclear technology is a symbol of modernity, the product of genius and danger, invention and fear. For the ancient Earth, it was simply another natural process, like volcanism or plate tectonics. The Oklo reactors remind us that the boundary between natural and artificial is thinner than we think. What we achieved in laboratories and reactors, the Earth had already achieved long before. And perhaps this is why Oklo remains so captivating. It was not just a scientific curiosity, but a window into the deep past, a past where our familiar world did not yet exist, and yet forces we associate with the modern age were already at play. A world where continents were forming, oxygen was rising, and nuclear fission was pulsing underground. For scientists, reconstructing this world is like piecing together a forgotten puzzle. Each detail matters. The isotopic ratios in Oklo's rocks tell us not only about the reactor itself, but about the atmosphere, the oceans, and the chemistry of the ancient Earth. They show us how geology, biology, and physics combine to create something unprecedented. And yet, with every answer comes another question. Was Oklo truly unique, or could similar reactors have existed elsewhere on Earth, their traces long since erased by erosion and time? Did nature conduct other nuclear experiments, hidden in places we may never find? And beyond our planet, could such reactors arise on other worlds given the right conditions? What is certain is that Oklo could not happen today. The uranium has aged, its fissionable isotope depleted. The chemistry of our world has changed. The window of possibility has closed. In that sense, Oklo was not only extraordinary, it was ephemeral, a fleeting chapter in the long story of the Earth. Cycles of fire and water. The genius of the Oklo reactors was not just that they existed, but that they worked in a way that seemed almost designed. They did not explode in uncontrolled fury, nor did they burn out in an instant. Instead, they pulsed, They breathed. They operated in cycles of fire and water, switching on and off with a rhythm that seems almost alive. To understand this, imagine the hidden chambers of Oklo 2 billion years ago. Deep underground, uranium-rich ore lay encased in sandstone and clay. Groundwater seeped into the cracks, filling voids, saturating the rock. As neutrons began to split uranium atoms, the fission reaction released enormous energy. Heat spread through the rock, and the water around it began to boil. Steam rose, bubbles hissed, the chamber crackled with invisible power. But as the water boiled away, something remarkable happened. Without water to moderate the neutrons, the chain reaction slowed and stopped. The fire went out, the reactor cooled, and then, as the temperature fell, water seeped back in, once again slowing the neutrons, once again setting the reaction in motion. Fire, then silence. Heat, then calm. A rhythm like a heartbeat, repeating over and over again. Modern scientists studying Oklo estimate that these cycles could have lasted hundreds of thousands of years. The reactor may have operated for intervals of about half an hour to several hours, producing steady bursts of energy before shutting down and restarting. It was, in every sense, a self-regulating system, an automatic nuclear engine built by nature itself. The parallels with human engineering are striking. In nuclear power plants, we design control rods, cooling systems and moderators to maintain stability. At Oklo, the Earth provided its own. Water acted as moderator and regulator, while geology provided containment. What human beings struggled to master in the 20th century, the planet had managed effortlessly in its youth, and the efficiency of this natural reactor was astonishing. Studies show that Oklo consumed about 5 tons of uranium-235 during its operation, producing energy equivalent to what a modern reactor might generate in years of operation. For millions of years, deep in the crust, this energy pulsed quietly, unseen, a reminder that the forces we wield today have always been part of the Earth's hidden arsenal. But the story does not end with energy alone. The byproducts of fission, elements like xenon, neodymium and plutonium, remained trapped in the rock. Incredibly, over billions of years, they have barely moved. Even plutonium, one of the most dangerous substances known to humanity, stayed locked within the mineral structure, immobilized by the Earth itself. For scientists, this is one of Oklo's most important lessons. If nature could contain nuclear waste safely for 2 billion years, perhaps we can too. Still, the most haunting aspect of Oklo is its rhythm. To picture a nuclear reactor starting and stopping on its own, cycling endlessly without oversight, is to glimpse a process that feels almost alive. Some have even described Oklo as the Earth's heartbeat, pulsing with energy in an age before complex life. It raises questions that touch not just on science, but on philosophy. Was this coincidence, or was it inevitability? Did nature simply stumble into the perfect conditions, or does the universe itself lean toward order, toward systems that sustain themselves? To walk through the mines of Oklo today is to sense that mystery. The pits are quiet, the stones ordinary to the eye. Yet hidden in their chemistry is the memory of cycles that burned long before humans appeared. It is as if the Earth itself were reminding us that power is not ours alone to command, that the forces we manipulate are part of a much deeper story, one that stretches back to the dawn of time. And here lies the paradox. Oklo was both fragile and enduring. Fragile because it required a unique set of conditions that may never align again. Enduring because it lasted for hundreds of thousands of years, its legacy preserved for billions. It was a phenomenon that belonged to a fleeting chapter of Earth's history, and yet one that speaks to eternal truths about matter, energy, and the balance of nature. The cycles of fire and water at Oklo were not just a curiosity. They were a demonstration, a proof that the laws of physics, given the right conditions, can build machines of staggering complexity without design, without intention, without us. Lessons for modern science. When scientists first realized what Oklo represented, they weren't just shocked, they were humbled. A nuclear reactor operating naturally, billions of years before humanity, was not only a scientific curiosity, it was a revelation. And from that revelation flowed lessons that continue to shape nuclear science, energy policy, and even our understanding of the Earth itself. The most immediate lesson was about nuclear waste. In modern times, one of the greatest challenges of nuclear power is what to do with the radioactive byproducts. Some remain dangerous for thousands of years, others persist for millions. How can we safely store such materials, ensuring that they don't leak into the environment, contaminate water, or harm future generations? These are questions that plague governments and scientists to this day. Oklo offered an answer, or at least a glimpse of one. When researchers studied the fission byproducts in the Oklo reactor zones, they discovered something astonishing. Elements like neodymium and ruthenium were locked into the rock in ratios identical to those found in man-made reactors. But even more importantly, the radioactive isotopes had barely moved in over 2 billion years. Plutonium, a substance feared for its persistence and toxicity, had remained essentially immobile, bound within the minerals. Nature, it seemed, had already performed a 2-billion-year experiment in nuclear waste storage, and the results were encouraging. This gave scientists confidence that deep geological storage could indeed work. If Oklo could contain nuclear byproducts for eons, then humanity might be able to replicate the process in engineered repositories, burying our waste in stable rock formations where it would remain secure. In this sense, Oklo was not only a window into the past, but a guide to the future, a natural demonstration project for long-term nuclear safety. But Oklo's lessons went deeper still. It reminded us that nuclear fission is not an unnatural invention, but a natural process. For decades, the public had feared nuclear power as something alien, dangerous, and artificial. Images of mushroom clouds and meltdowns dominated the imagination. Yet here was proof that the Earth itself had once run on nuclear power, quietly and safely, without catastrophe. In a world starved for clean energy, this realization carried symbolic weight. Nuclear power, though risky in human hands, was also part of the planet's own history. At the same time, Oklo forced scientists to refine their understanding of nuclear physics. By studying the isotopic signatures in the rocks, researchers were able to test theories of fundamental constants, those unchanging numbers that define the laws of the universe. Some even used Oklo as a laboratory to ask, have the laws of physics themselves been constant over time? Remarkably, the isotopic evidence suggested they had. The fine structure constant, which governs the strength of electromagnetic interactions, appeared unchanged after 2 billion years of nuclear operation. Oklo thus became not only a reactor, but a cosmic clock ticking across deep time. And yet Oklo's lessons were not purely technical, they were philosophical. It reminded us of the humility required when confronting nature. The achievements of our species, splitting the atom, harnessing the nucleus, feel monumental. But Oklo whispers a different truth. We were not the first. Long before we understood the atom, the Earth itself had mastered it. Long before our reactors lit cities, a natural reactor pulsed in darkness, unseen and uncelebrated. For some, this humbling fact inspired wonder. If nature could build a nuclear reactor, what other marvels might lie hidden in the deep history of the Earth? For others, it stirred unease. If nuclear fission is natural, perhaps its dangers are also inevitable. Perhaps radiation, reactors, and waste are not intrusions into nature, but part of its fabric. Either way, the discovery reshaped our relationship to the atom. Practical, symbolic, philosophical, the lessons of Oklo echo in every debate about nuclear power today. They caution us about waste, reassure us about containment, and remind us that fission is not merely a human experiment, but a natural phenomenon. And they challenge us to think in longer timescales, not years or centuries, but millions and billions of years, the scale at which the Earth itself works. Yet for all its answers, Oklo left mysteries unresolved. Was it truly a unique event, or one example among many, erased by time? Was it pure chance, or an inevitable outcome of physics and geology? And beyond Earth, could such reactors exist elsewhere? On Mars, on moons, on planets circling other stars, mysteries and speculations. Even after decades of study, Oklo remains as much a mystery as it is a marvel. The science is clear. Nuclear fission happened there, naturally, 2 billion years ago. The isotopic signatures, the depleted uranium-235, the trapped byproducts, all the evidence is beyond dispute. But the deeper we look, the more questions we find. Questions that drift from geology into philosophy, from physics into speculation. The first mystery is uniqueness. Why Oklo? Why there in Gabon, and not in other uranium-rich deposits around the world? Uranium exists on every continent, in ores scattered across the globe. And 2 billion years ago, its isotopic composition was the same everywhere. So why did reactors ignite at Oklo and nowhere else? Was it purely chance, a perfect alignment of geology, chemistry, and hydrology that happened once in the entire history of Earth? Or were there other natural reactors, hidden in deep time, whose traces have been erased by erosion, metamorphism, or tectonic shifts? If so, Oklo may not be an isolated miracle, but one survivor of a forgotten pattern, a reminder that nature may harbor secrets still waiting to be uncovered. The second mystery is purpose. Some cannot resist asking whether Oklo was truly an accident of nature or something more. After all, the conditions were precise: uranium enriched to just the right level, water flowing at just the right pace, geometry perfectly balanced to sustain a reaction without catastrophe. To skeptics, this is simply the inevitable consequence of physics. To others, it feels uncanny, almost as though the Earth itself was conducting an experiment. Some fringe voices have even speculated about intervention, that perhaps Oklo was designed not by humans, but by something older, something beyond us. Mainstream science rejects such ideas, but the fact that they persist reveals just how extraordinary Oklo appears to the human imagination. The third mystery reaches beyond Earth. If a natural reactor could arise here, why not elsewhere? Could Mars, rich in uranium, once have harbored its own fission zones? Could exoplanets, orbiting distant stars, bear similar scars of natural reactors buried in alien crusts? If so, Oklo is not just a geological curiosity, it is a cosmic possibility, a hint that nuclear energy might emerge wherever conditions allow, shaping the histories of worlds we have never seen. And then there are the implications for life itself. Some researchers have speculated that natural reactors like Oklo could have influenced the evolution of early life. Radiation, after all, can damage DNA, but it can also drive mutation, the raw material of evolution. Could pulses of radiation from Oklo's cycles have affected microbial life in ancient Gabon, accelerating change, pushing biology in directions it might not otherwise have taken? There is no direct evidence, but the possibility lingers, another thread in the tapestry of speculation. Finally, there is the philosophical mystery. Oklo forces us to reconsider our assumptions about what is natural and what is artificial. We think of nuclear power as the pinnacle of human ingenuity, a technology fraught with danger and promise. Yet Oklo shows us that fission is not ours alone to command. It belongs to the Earth, to the universe, to physics itself. What we build with rods and reactors, nature once built with stone and water. The line between invention and discovery blurs. We did not create nuclear power. We found it, already written into the fabric of the world. And so the Oklo reactor lingers in our imagination, suspended between certainty and wonder. It is proof of what happened, and a question about why it happened. It is a laboratory for nuclear science, and a riddle that defies simple answers. It is a reminder that our planet is stranger than we know, that its depths hold stories beyond our reckoning. Perhaps the greatest mystery of Oklo is not how it worked, but what it means. Was it a cosmic accident, a geological fluke, a one-time miracle never to be repeated? Or was it something deeper, a sign that the universe leans toward order, that matter itself seeks balance, that even in the silence of a young Earth, the laws of physics were writing stories beyond imagination? We may never know. But to stand at Oklo is to feel that question pressing against you, to sense that the stones remember something we have only begun to understand. A power plant, older than humanity. The sun sets over the forests of Gabon, and the land falls into quiet shadow. To the untrained eye, there is nothing unusual here, just earth and stone, the remnants of old mining pits overgrown by grass and time. Yet beneath these ordinary surfaces lies one of the most extraordinary stories ever uncovered in the history of science. For here, 2 billion years ago, the Earth itself built a nuclear reactor. Think about what that means. Long before humans harnessed fire, long before mammals roamed the land, before even the first multicellular life flourished in the oceans, this planet was already running on nuclear power. Not in a city, not in a laboratory, but in silence, in darkness, in stone. The Oklo reactors defy not only our expectations of geology, but our sense of human uniqueness. We are not the first to harness the atom. We are not even the first to build a reactor. The Earth did it long before us. This revelation changes everything. It changes how we think about nuclear science, about waste, about safety, about the very laws of physics. Oklo shows us that the atom is not ours alone to command. It is part of nature, part of the universe, a force written into the fabric of matter itself. What we think of as technology may sometimes be discovery, an unveiling of processes that were already there, waiting to be found. But Oklo also leaves us with questions that no science can fully answer. Was it a miracle of chance? A geological fluke that happened once and never again? Or was it inevitable, the natural outcome of physics in a world where uranium-235 was still abundant and water flowed through stone? If it happened here, could it happen elsewhere? Could there be reactors hidden in the rocks of Mars or pulsing beneath the crust of distant planets, running silently through alien ages? And then there is the meaning for us. Here and now. For centuries, humanity has feared nuclear power as both promise and peril. We see in it the brilliance of energy and the shadow of destruction. But Oklo reminds us that fission is older than fear, older than us. It is not unnatural. It is as much a part of the earth as volcanoes or lightning or tides. It is power, raw and real, indifferent to our judgments. Perhaps the true lesson of Oklo is humility. We pride ourselves on our mastery of nature, on bending atoms and stars to our will. Yet this story whispers otherwise. The Earth is older, wiser, stranger than we know. It carries secrets that dwarf our achievements, patterns that echo across eons, mysteries carved in stone. Oklo is one such mystery, a reminder that the universe has already walked paths we think are new. And so we return to the silence of Gabon, to the quiet mines where grass now grows. Beneath your feet, isotopes whisper of ancient fire, of cycles of fission and rest, of a heartbeat that pulsed for hundreds of thousands of years. You cannot see it, you cannot hear it, but it is there, written in the chemistry of stone, proof that nature once lit its own reactor, a power plant older than humanity itself. What does this mean for us? Perhaps it is a warning that the forces we wield are not to be taken lightly, for they belong to the earth itself. Perhaps it is reassurance that nature can manage what we fear, containing its waste safely for billions of years. Or perhaps it is an invitation to wonder, to curiosity, to awe at a planet still filled with secrets beyond our grasp. The Oklo reactor is gone now, its fires long extinguished, but the questions it raised remain alive. Was it accident or design? A fluke of geology or a glimpse of universal law? A road to nowhere or a window into the hidden heart of the cosmos? We may never know. But to stand at Oklo, to walk upon that ground, is to feel a connection across time, to a world 2 billion years past, to a power that predates humanity, to a mystery that humbles and inspires. So we leave Gabon with more questions than answers, with wonder heavy in our minds and awe deep in our bones. The earth, it seems, is more than stone and water. It is an engine of miracles, a keeper of secrets, a builder of reactors that burn in silence for millions of years. And so I ask you, what do you believe? Was Oklo chance, inevitability, or something more? A natural accident or a cosmic message written in stone? Share your thoughts in the comments, because the story of Oklo is not finished. It lives on in us, in our science, in our imagination, and in the questions we continue to ask, because sometimes the greatest mysteries are not out there among the stars. Sometimes they are beneath our feet, hidden in the very bones of the earth.